Have you ever wondered what would happen if the Earth suddenly stopped spinning? We live as if everything is steady, streets stay where they are, oceans stay inside their shores. The sky keeps its familiar rhythm. But beneath that calm surface, our planet is turning non-stop, and it has been turning for so long that our bodies treat it like silence. Tonight's question is simple. If rotation is so powerful that it shapes days, weather, and the very way we move through space, why does the universe seem to love spinning at every scale? From a child's spinning top to a planet's axis, from a star system forming out of a swirling cloud to a galaxy turning like a slow wheel of light, the same theme keeps returning. And the stranger part is this: most of the time, we don't feel any of it. Stay with me, and you'll get a clear, easy picture of why almost nothing truly stops once it starts spinning. Why rotation tends to persist, grow, and spread from small objects you can hold to structures so large they take hundreds of millions of years to complete a single turn. Along the way, you'll hear real moments that made people rethink motion. A pendulum in 1851, quietly revealing Earth's rotation. A mysterious radio pulse in 1967 that turned out to be a spinning star, and a 2019 image that showed a shadow shaped by an extreme cosmic whirl. No equations, just a calm journey through the universe's most persistent habit. Maybe the strangest part is that nothing has changed since you pressed play. You are still lying or sitting wherever you are, and yet, while you stay, everything underneath you is quietly in motion. You wake up. For a moment, you are just a body in a familiar room. Ceiling, wall, phone screen, the edge of the bed. Nothing in that picture suggests speed. The floor does not hum. The window does not blur. If someone told you right then that you are riding a spinning world, you could nod politely and still not feel it in your bones. You swing your legs over the side of the bed and sit up. The mattress creaks. The air is still. There is no roar of engine, no wind against your face. And yet, if you lived at Earth's equator, the ground beneath you would be turning eastward at about 1,600 kilometers an hour. Faster than a jet, faster than sound. The room is part of a giant rotating sphere, but the water in your glass does not slosh to one side. The curtains do not lean. You stand. You walk to the bathroom. Lights flick on. A mirror stares back. You brush your teeth. The most dramatic thing happening is maybe the way the toothpaste foams a little too much. Meanwhile, that spinning planet is also falling around the sun in a huge, nearly circular path. One full loop every year. That motion carries you along as well. Whether or not you remembered to brush in small circles, far beyond that, the sun itself is not fixed. It is tracing a slow orbit around the center of the Milky Way, taking roughly 225 to 250 million years to complete a single lap. In that time, continents shift. Species appear and vanish. Whole mountain ranges rise and erode. Your star circles once, and everything on its surface writes an era. And the galaxy that holds it all is not staying put either. The Milky Way drifts inside a small cluster of galaxies called the local group, moving through space under the pull of gravity, bending and being bent by its neighbors. So, before you even finish your first cup of coffee, you are being carried along by at least 4 layered motions. The spin of Earth, its orbit around the sun's path around the galaxy, and the galaxy's slow drift among others. The more of these background motions we add, the stranger the silence becomes. Because nothing in your body raises an alarm. No inner voice says, "Careful, you are in a system spinning and falling through space." The chair does not vibrate. Your hands do not shake. Life feels stationary. It is a quiet paradox. The greater the motion in the background, the more completely it disappears from your everyday sense of stillness. If humans had only trusted their skin and stomachs, we might still believe the universe revolves neatly around us. For most of history, we did. The ground felt still. The sky turned. That was obvious. Why question it? It took a very particular kind of stubborn curiosity to ask, what if the feeling is wrong? In January of 1851, in Paris, a man named Léon Foucault decided to make the question visible. He did not climb a mountain or leave the planet. He walked into the Panthéon, a grand stone building, and hung a heavy metal bob from a long cable attached high up in the dome. Just a simple pendulum, a weight, a wire, and gravity. If you give a pendulum a gentle push, it swings back and forth in a plane, left-right, tracing the same line again and again. Foucault's idea was quiet and radical. The swinging plane would try to stay fixed in space, while Earth rotated beneath it. Imagine standing under that dome on a cold morning as they pull the bob to the side and release it. At first, it seems ordinary. The weight slices through the air, back and forth, over a circle of sand. But as minutes become hours, something unsettling appears. The line of the swing seems to drift. Each pass cuts the sand at a slightly different angle. Tiny markers placed around the circle begin to fall, one by one, knocked over by the slow turning of the swing's path. Of course, the pendulum is not changing direction. You are. The floor is. The building. The city. The entire planet. What you are actually seeing is Earth itself rotating, revealed not by a spinning sky, but by the quiet insistence of a swinging mass that refuses to follow the ground's motion. If you spent the whole day there, barely moving, you would experience a kind of inverted astronomy. No telescope, no stars, just one line of motion on the sand, slowly proofing that the world is turning beneath your feet. Many science museums and public spaces still host versions of Foucault's pendulum. They hang from high ceilings, cutting long circles through the air while visitors walk below. Sometimes there are pegs around the base, and every so often one of them is knocked down, as if some invisible hand has nudged the swing sideways. People stand, watch, and drift away. The pendulum continues, patient, indifferent to attention. Every once in a while, the mechanism that keeps it moving fails. The pendulum slows, then stops. The cable hangs motionless. Local news runs a tiny story. Foucault pendulum halts after decades. There is always a hint of drama in the headline, as if the planet itself has briefly taken a break, as if rotation and story must be linked. But Earth, of course, has not paused for a single heartbeat. Only the human machine has. We even carry this idea into our imagined futures. When filmmakers try to picture a place where humans can live in artificial gravity, far from home, they often build a spinning wheel. In the 1968 film 2001, A Space Odyssey, a vast circular station turns in the blackness. Inside, people walk along its inner rim, feet pressed outward by the station's spin. To them, down is always away from the center, created by what we call centrifugal force. There are no rocket engines firing to pin them to the floor, just rotation. By spinning the structure, the film gives its characters a sense of weight, of normalcy, of stillness. It is a beautiful contradiction. In order to make viewers feel that life in space could feel ordinary, the director reaches for rotation, a wheel turning in a void, so that people inside can sit, drink, sleep, and forget they are falling. Closer to Earth, the metaphor shows up in smaller ways. Think of a moving escalator. You step on, stand still, and yet the world slides past. The stairs hum, the handrail glides under your fingers. Your body is doing almost nothing, but your position is constantly changing. Scale that idea up. The universe becomes a system of nested escalators, each one carrying the next. The step you stand on is Earth's surface. That step rides a larger one, the planet's orbit around the Sunday. That entire machine is being transported on the moving track of the Sun's galactic orbit. which itself is riding the slow conveyor of the Milky Way's drift through space. You rarely feel any of that, for the same reason you barely feel an escalator that moves smoothly. Your body pays attention to changes, to bumps, to sudden accelerations and jolts and turns. Constant motion goes invisible. Physics has a way of making this intuition precise. If a motion is uniform and straight, or a rotation is perfectly steady, your inner ear has very little to complain about. The fluid in its tiny curved canals is not being sloshed back and forth. The signals to your brain say, more or less, all quiet. The same thing happens on a long flight. Once the plane levels out and cruises at a nearly constant speed, the roar settles into background noise. You might look out the window and see the ground sliding by below. But if the window were covered, your body would not insist that you are moving at close to 900 kilometers an hour. You can sip a drink, close your eyes, drift off. For your nervous system, smooth motion quickly becomes the new normal. Earth's rotation is, from your point of view, the smoothest flight you will ever take. There are no sudden starts or stops, no corners, no braking, just a continuous turning that has been going on since long before there were humans to notice. Gravity holds the atmosphere and the oceans close, turning them with the planet, so there is no colossal wind from east to west, no constant sideways pull. Everything around you is part of the same ride, so the ceiling looks steady, the lamp hangs straight. Your heartbeat is the only rhythm you really hear. That is the strange starting point for this journey. You live on a spinning platform. That platform orbits a star. That star circles a galactic center. The galaxy itself is in motion, and yet the experience you call stillness is built on layers and layers of motion that never ask for your consent. The question that waits underneath is quiet, but it does not go away. If our entire floor is moving and we never feel the push, then where did all this spinning come from? And why does it seem so determined to keep going? Maybe the easiest way to answer that question is not to look up at the sky yet, but to watch a human being turning on a sheet of ice. Picture a figure skater gliding to the center of the rink. The arena is dim, the air a little cold, the crowd murmuring. She pushes off, gathers speed, and then pulls her body tight into a spin. Arms tucked in, legs drawn close. Her rotation suddenly sharpens. In a heartbeat, she goes from a slow, graceful turn to a blur. When she wants to slow back down, she simply unfolds. Arms open, one leg extended, and the spin softens into a gentle rotation. Nothing mysterious has entered or left her body in that moment. No engine switched on. No invisible hand grabbed her and twisted. All she did was rearrange herself. When she pulls in, her mass is concentrated closer to the axis of spin, so the turning speeds up. When she stretches out, she spreads that mass farther from the axis, and the same turning effort produces a slower spin. You do not need the name of the law to feel the rule. Keep the spin the same. Bring things inward, everything turns faster. Push things outward, everything turns slower. Once the rotation is there, it is stubborn. The skater does not need to keep pushing. She can almost relax into the spin, and it continues until friction in the ice and air finally steals it away. Now, take that same intuition and lift it off the ice. Imagine, not a person, but a vast cloud of gas in space. Cold, barely glowing, drifting between the stars. It stretches across many light years, so large that it would take light itself years to cross from one side to the other. Inside, particles of hydrogen and dust float in slow, random motion. From far away, you might say this cloud is almost not rotating at all. Maybe there is a tiny tendency for it to drift in one direction rather than another, a slight preference you could easily miss. But perfection is rare. There is almost always some small asymmetry, a little more material here than there, a slight imbalance in how atoms move. Now let gravity begin to win. The cloud starts to collapse inward, not all at once, and not perfectly, but enough that the whole structure begins to shrink. As it shrinks, something familiar happens. Just like the skater pulling her arms in, the cloud's slight initial rotation is squeezed into a smaller radius. The spin speeds up, very slowly at first, then more and more as gas falls inward. What began as an almost unnoticeable turn becomes a clear rotation. The cloud flattens into a disk because material moving in circles naturally settles into a plane. At the center, matter piles up into a dense core that will one day ignite as a star. Around it, the remaining gas and dust orbit in a broad, spinning sheet. The rule is the same as on the ice, just scaled up beyond anything we can see directly. A tiny hint of spin, plus collapse, equals a much stronger rotation. The universe does not need to add extra twisting from outside. It just needs a cloud that is not perfectly still and some time for gravity to tug everything inward. In this sense, stars, planets, and the glowing disks around young suns are all enlarged versions of that skating move. A small, initial swirl gets amplified as material falls toward the center. If the cloud had truly zero rotation, and if every push and pull were perfectly balanced, no disk would form. But real clouds are messy. Real motions are slightly off. So disks form almost everywhere. Humans learned this rule not only from watching the sky, but from our own attempts to stay oriented in space. Think about early satellites. The first generations were simple metal cylinders and boxes launched into orbit with just enough electronics tucked inside to send back data. Engineers needed a way to keep these fragile machines pointed in roughly the right direction without constantly firing thrusters. Fuel was precious. Complexity was risky. One elegant solution was simply to spin the whole satellite. Imagine a silver soda can floating high above Earth, gently rotating around its long axis. As it spins, that axis becomes oddly stubborn. It resists being twisted or tipped. Random nudges from sunlight, thin traces of atmosphere, or small gravitational tugs have a harder time making it wobble. The spin acts like a stabilizing gyroscope, keeping the satellite's nose pointing where it should. As long as nothing drains that spin too quickly, the satellite can keep its orientation with minimal intervention. Again, once rotation is there, it wants to stay. You have seen the same principle in toys. A spinning top stands upright when turning fast, then begins to wobble and fall as it slows. A toy gyroscope, when wound up and placed on a string or the edge of a table, hangs in positions that look impossible. Its spinning wheel locks its axis in a particular direction, and the weight tries to pull it elsewhere. And the result is that strange, stubborn balance. Take a bicycle wheel. Hold the axle loosely in both hands. When the wheel is still, you can easily twist it in any direction. Spin it up though, and it suddenly fights you. Try to tilt it, and you feel an odd sideways push. The wheel wants to keep its axis pointing the same way in space, even while your hands are trying to reorient it. This is why gyroscopes show up everywhere in our technology. In older aircraft, mechanical gyros whirled inside instruments to give pilots a stable reference for up and down, ignoring the turbulence outside. In spacecraft, spinning mass wheels or gyros help keep antennas and solar panels facing the right way without burning through fuel. Even in your phone, tiny electronic versions of gyroscopes sense how you tilt or rotate the device, so the screen can flip and games can respond. Hidden inside these machines is the same quiet rule. A spinning object resists changes to its orientation. The faster it spins and the more mass it has, the more stubborn it becomes. When physicists took this idea to its limit, they found something even stranger. Not only do spinning objects resist being reoriented inside spacetime, but rotation itself can twist spacetime around them. In the early 2000s, a mission called Gravity Probe B was launched to test a delicate prediction of Einstein's general relativity. The idea was to put some of the most precise gyroscopes ever built into orbit around Earth, and then watch whether their axes drifted in very specific ways over time. The satellite carried 4 spheres, each almost perfectly round, spinning quietly in a near vacuum. If only the familiar kind of gravity were at work, their axes would point in nearly fixed directions relative to the distant stars. But Einstein's theory said there should be 2 subtle effects. One from the way Earth's mass curves space-time, and another from the way Earth's rotation drags space-time along with it, like honey swirling around a spoon. For years, the team measured tiny changes in the directions those spinning spheres pointed. The analysis was difficult. Noise crept in. But eventually, around 2011, the results came together. The gyroscopes had drifted just as Einstein's equations predicted. Not only was space-time curved by mass, it was also slightly twisted around a spinning planet. At that point, the earlier intuition becomes even deeper. A spinning object does not just resist being turned. It participates in shaping the stage it spins on. You can feel a faint echo of this stubbornness in your own body when you turn too fast. Stand in an open space, away from fragile things. Spin yourself around a few times with your arms stretched out. Then pull your arms in close as you keep turning. You will feel the rotation quicken, your body drawing itself into a tighter, faster whirl. When you stop abruptly, your inner ear keeps insisting that you are still turning. The fluid in those curved canals continues to move, and your brain interprets that movement as rotation. The result is dizziness. The room seems to swing. Your sense of balance lags behind reality. In a small, inconvenient way, your body is having to manage the same problem that stars and planets face in a grand, serene way. Once rotation is present, it does not want to vanish. Your inner ear needs a moment for friction to settle the fluid. Planets need countless collisions and tidal forces to slow their spins. Galaxies, with their enormous masses and relatively empty surroundings, hold onto their rotation for billions of years. The universe, as far as we can tell, does not come with a universal handbrake. There is no cosmic friction that automatically brings every motion to rest. Instead, there are local ways to lose rotation: rubbing surfaces, turbulent gas, magnetic fields, tides, impacts. Every time two systems interact, some of their orderly spin can be converted into heat or broken into more chaotic motion. But unless those interactions are strong and repeated, the rotation persists. A planet that spins today will still be turning tomorrow, and for many millions of tomorrows, only gradually slowed by the tides it raises in its own oceans. A star that formed from a collapsing cloud will carry part of that cloud's spin for the rest of its life. A galaxy that gathered its rotation from countless collapsing regions and mergers will keep wheeling through space long after its brightest stars have faded. From skaters to satellites, from toys to gyroscopes in orbit, the pattern is the same. Give something even a little spin, and do not constantly steal that spin away. And it will keep turning. Shrink it, and the rotation sharpens. Try to twist its axis, and it resists. Wrap space-time around it, and the geometry itself carries a memory of the spin. In everyday language, you could say, motion likes to keep going the way it is already going, and spin is motion that has folded itself into a circle. The world does not need a new push every second to keep revolving. It only needs an absence of strong reasons to stop. Which brings us back to that collapsing gas cloud. A slight imbalance here. A gentle swirl there. Gravity pulling inward on an enormous scale. Each piece of the cloud moving in response. Circling. Tightening. Speeding up. Local friction within the cloud redistributes some of the spin. Magnetic fields tangle and carry angular momentum outward. Fragments separate and form their own smaller disks. But the essential rule holds. A tiny initial asymmetry plus collapse generates a spinning structure. If that is how the story begins for a single star and its planets, it hints at a larger pattern. Maybe the universe did not decide that everything should spin. Maybe rotation is simply what happens when matter falls inward without being perfectly, impossibly balanced. We now have, at least, the outline of a rule. Once spinning starts, it is hard to stop. When something big shrinks, its spin tends to intensify. When you try to twist a spinning thing, it pushes back. And if you give a cloud a little swirl and let gravity do its work, you are almost guaranteed to get a disk. The next question is wider and more concrete. If this is the rule at the heart of all these motions, then how exactly does it shape the birth of real systems? How do those collapsing, spinning clouds turn into the particular stars, planets, and even galaxies we see? And what traces of that original spin are still written into their orbits today? Maybe the best way to answer that is to turn the lights down even further and follow a single cloud of darkness to where a star has not yet been born. Far out in the arm of a galaxy, there is a place where the stars thin out and the night grows strangely deeper. Not deeper because there are fewer stars, but because something is hiding them. A cold, heavy cloud hangs there, stretching across tens of light years. To the eye, invisible light, it is almost nothing. A faint smudge, a patch of sky where brightness seems to have been erased. Inside that darkness, hydrogen gas and microscopic dust grains drift in slow, quiet motion. The temperature is only a few degrees above absolute zero. No clear boundaries, no neat sphere or disk, just a tangled volume of slightly denser and slightly thinner patches. If you could float there, your eyes would never adjust. It would be too dim for vision, too cold for comfort, too empty for sound. This is a pre-stellar cloud, a waiting room for stars. At first glance, it does not look like anything special. Similar clouds exist all over the galaxy. Some will break apart, some will be stirred and diluted by shock waves from distant explosions. Some may remain quiet for ages. But somewhere inside this one, gravity is beginning to win a small argument. In a slightly denser knot, the pull inward is just a little stronger than the push outward of gas pressure. As atoms jostle and collide, their random motions are not enough to keep the region puffed up. It starts to sink into itself. Slowly, over hundreds of thousands of years, then over millions, the knot grows denser, pulling in more and more of the surrounding material. From far away, you would see the whole cloud change shape. It contracts, not like a balloon deflating, but like fog thickening at its center. And as it shrinks, the rule from before quietly asserts itself. This cloud is not perfectly still. There is a tiny net rotation, a preference for swirling a little more one way than the other. It might be so mild at first that no human instrument could have measured it. But gravity does not care about how small it starts. As the cloud collapses, that faint swirl is squeezed inward. The rotation speeds up. The more material falls toward the center, the more the cloud flattens, turning from a roughly rounded shape into something more like a thick disc. Imagine dough on a baker's hands. She places a lump on the counter, then spins it gently. As it turns, it spreads outward into a flat, round sheet. The mass has nowhere else to go. Rotation favors the wide, shallow shape over the tall, narrow one. The forming star system behaves in a similar way, only without a countertop, without hands, without air. Just gravity, motion, and time. At the very center of the disk, matter piles up. Every infalling stream, every spiral of gas, overshoots a little, collides with itself, and loses energy. The core grows denser, hotter, more pressurized. At some point, deep inside that hidden heart, the temperature and density cross a threshold. Hydrogen nuclei begin to fuse into helium, releasing energy. A star switches on. From the outside, the birth is not a sudden flash like a fireworks burst. It is the slow brightening of a point that was once almost invisible. The new star shines first in infrared, warming and dispersing the shroud around it. Eventually, as the surrounding dust thins, its light leaks out in visible wavelengths. The story around that star is not finished, though. The disk remains. In that spinning sheet of gas and dust, small grains begin to stick together. Dust motes collide and cling through electrostatic forces, forming larger clumps. Those clumps bump and merge into pebbles, then boulders, then mountain-sized chunks. Gravity starts to matter on that smaller scale too. Once an object grows large enough, its own pull helps it sweep up material, carving lanes in the gas, drawing in debris like a quiet vacuum cleaner. All the while, the whole system is rotating. Every particle, every ice chunk, every rocky embryo circles the central young star in the same general direction. inherited from the original spin of the collapsing cloud. This rotation both shapes and limits their dance. It keeps them in roughly the same plane, like marbles rolling in a shallow bowl instead of flying off in random directions. Over time, a kind of competition plays out. Some growing bodies accrete more and more material and become planets. Others lose the race, broken apart in collisions or swallowed by larger neighbors. Gas giants form farther out, where hydrogen and helium can remain bound in thick envelopes. Rocky worlds coalesce closer in, where it is too warm for light gases to be easily held. Moons take shape from leftover fragments around planets. Asteroids and comets linger as persistent rubble, relics of building that never found their way into a finished world. For a long while, these processes were only theories. Equations, diagrams, sketches in textbooks. But in the last few decades, telescopes have started to show us these disks directly. When you look at certain images from observatories like the Atacama Large Millimeter Array or the space telescopes that see in infrared, you find something startling. Young stars, wrapped in luminous rings of dust, with darker gaps carved into them. Those gaps are not decorative. They are traces of planets still forming, carving paths as they orbit, sweeping out the material in their way. The light we capture from those structures is, essentially, a snapshot of star and planet formation in action. Not in some other hypothetical universe. In ours. Right now, you do not need the technical vocabulary. It is enough to know that we are literally watching planet farms in the sky. Circular fields of gas and dust being plowed and rearranged by invisible worlds that have not finished growing. Our own system once looked like that. Long before there was an Earth with oceans and continents and people, there was a young sun surrounded by a rotating disk of gas and dust. That was about 4.5 billion years ago, when the galaxy itself was younger, and the local neighborhood looked different. Within that disk, most of the material spiraled inward to feed the Sunday. Some condensed into the rocky inner planets. Some gathered far out into the gas giants and their icy moons. Some remained as belts of smaller objects. The asteroids between Mars and Jupiter. The icy bodies of the Kuiper region beyond Neptune. The distant reservoir of comets. The fact that almost all the major planets orbit in roughly the same plane, and in the same direction, is not an accident. It is a fingerprint, a frozen memory of the original spin of that primordial disk. When you see the planets lined up in a diagram, gently looping around the sun in a common direction, you are looking at the afterimage of a cloud that collapsed and flattened and spun. Rotation did not just move things around. It set the conditions for which worlds could form where. Closer to the sun, where the heat was intense, lighter materials like water and methane had a hard time remaining in solid form. Heavy elements and rock dominated. That is why the innermost planets are small and dense, their surfaces made of silicates and metals. Farther out, beyond a certain distance, temperatures dropped enough for ices to survive. There, giant cores of rock and ice could gather thick blankets of hydrogen and helium, becoming the swollen gas planets. Position in the disk mattered not only for composition, but for potential habitability. Too close to the star, and any surface water would boil away. Too far, and it would freeze solid. Somewhere in between lies a band where liquid water can persist on a rocky surface, given the right atmosphere. A region that came to be called, later, the habitable zone. Earth grew inside that band. Not exactly at its center, not on some privileged line, but in a region where the balance turned out to be surprisingly gentle. A world neither too heavy nor too light, neither locked to its star nor tumbling chaotically, with a rotation that gives day and night a moderate rhythm rather than extremes of infinite noon or endless dusk. It is easy to look at that balance and search for intent, to feel that just right must mean chosen. The physics does not require that, but it does suggest something quieter. Rotation and distance and chance can combine to open narrow windows where complexity survives. Our planet's spin is part of that story. A full turn, roughly every 24 hours, gives the surface time to warm in daylight and cool at night. Without locking half the world into perpetual frost, and the other half into constant blaze. The rotation also helps shape weather patterns, ocean currents, and the shielding magnetic field that rises from the spinning, conducting core. Change the spin enough, and the whole pattern of climate and habitability shifts. Other planets in our system display different outcomes of the same general process. Mars spins at a similar rate but lost most of its atmosphere. Venus rotates slowly and in the opposite direction compared to most planets. Its day lasting longer than its year, its surface buried under a crushing, heat-trapping blanket. Gas giants spin quickly, their days rushing past in hours, with atmospheres whipped into towering storms. All of these worlds emerged from the same rotating disk. Selection did not happen in a conscious sense, but in a physical one. Each orbit and spin is a path carved out of the space of possibilities, favored by local conditions and by accidents of collision. Many combinations do not last. A few do. When we imagine more extreme disks, far from home, the same shapes appear again, rotated into something more violent. In the film Interstellar, there is a now famous image of a black hole called Gargantua, encircled by a glowing, warped ring of matter. That ring is an accretion disk, a cousin of the disks around young stars, only pushed to a terrifying extreme. Gas spirals in at a significant fraction of the speed of light, heated to incredible temperatures, its light bent and lensed by the intense gravity. The result is a kind of burning halo around darkness, a whirlpool of energy and spin. What made that image resonate so strongly is not just the drama, but the fact that it was grounded in real physics. The team behind it used actual equations of general relativity and accretion flows to calculate how such a disk would look. The shape on the screen is not pure fantasy. It is a visualization of the same rule, collapse plus rotation, operating near an object so compact that even light can be trapped. From quiet, pre-stellar clouds to ferocious disks around black holes, the pattern repeats. Matter falls inward. If there is even a hint of angular momentum, the infalling material cannot simply plunge straight down. It must orbit. It must spread into a disk. And in those disks, new things can be assembled. Stars, planets, jets, flares, storms. The little family of worlds around our sun is one such arrangement. But seen against the backdrop of the galaxy, it is a speck, a grain of sand in a much larger wheel. Because above this scene of collapsing clouds and spinning disks lies a structure that has been turning for billions of years, the galaxy itself. Hundreds of billions of stars, each with their own histories and orbits, all participating in a broader rotation. If a single cloud's tiny spin can shape the birth of a star and its planets, what happens when you scale up to a city of stars? When the disk is not a few hundred astronomical units across, but tens of thousands of light years wide? What does rotation look like when it is written not in dust and pebbles, but in suns? When you step back far enough, the disks of dust and planets start to blur, and what is left on the canvas are larger wheels, each one made of cities of light. Imagine floating far above a spiral galaxy, high enough and distant enough that the whole structure fits comfortably into your field of view. At the center there is a swollen glow, a bulge where stars crowd together so densely that their light blends into a soft core. From that core, arms unfurl. They curl outward in slow, elegant curves, bright with young blue stars and dotted with pinkish knots of glowing gas. Dark lanes of dust thread between them like smoke, cutting sharp shadows into the luminous swirl. The entire thing is not a still picture. It is turning. Every star you see in that disk, every hidden cloud, every cluster is in motion around the center. The inner regions complete their loops more quickly. The outer ones sweep along on more leisurely paths. Together, they form a colossal rotating disk of light, a wheel tens of thousands of light years across, holding hundreds of billions of stars. If our intuitive sense of orbits were right, that would be where the story ends. We are used to the pattern of a planetary system, where the closest planets whip around the star in short, fast years, and the outer planets move more slowly and take far longer to complete a single orbit. That pattern fits nicely with a simple reading of gravity. The farther you are from the central mass, the weaker the pull, and the slower you ought to move to remain in a stable orbit. For a long time, astronomers assumed galaxies would behave the same way. Stars near the galactic center should travel quickly. Stars in the outskirts should crawl. If you graphed their orbital speeds as a function of distance, you would expect a curve that rises near the center, peaks, and then declines, as if the galaxy's outer reaches were moving in slow, graceful arcs. But when we began to measure those speeds carefully, the galaxy refused to cooperate. By tracking the light from stars and the radio glow of gas, scientists mapped how fast different parts of a galactic disk rotate. They expected to see the velocities drop with distance. Instead, beyond a certain radius, the speeds leveled out. Stars far from the center were circling almost as fast as those closer in. The rotation curves, as they are called, were not falling. They were nearly flat. In ordinary language, that means the outer disk is whipping around much faster than seems reasonable, given the amount of visible mass that appears to be holding it in. If you take only the luminous matter into account, the stars, the glowing gas, the dust you can infer from how it blocks starlight, the gravitational pull it generates is not enough to keep those rapidly moving outer stars bound. They should drift away. Over cosmic time, the galaxy should slowly fling its outer regions into space, unraveling like a spinning wheel whose spokes have been removed. And yet, that is not what happens. The outer stars stay. The spiral arms persist. Galaxies that are billions of years old are still recognizable structures. Whatever is keeping them together is doing so quietly and reliably. This is the problem that led to one of the strangest conclusions in modern astronomy. Most of the matter in a galaxy does not shine. To make sense of those flat rotation curves, you have to add mass that does not emit or reflect light in any way we can easily detect. It does not glow in visible wavelengths, nor in radio, nor in X-rays. It passes through ordinary matter without interacting much at all. The only clear way it reveals itself is through gravity. We call it dark matter, not because it is sinister, but because it is opaque to light and largely opaque to our understanding. Model a spiral galaxy as not just a thin disk of stars, but as a bright disk embedded in a much larger, nearly spherical halo of invisible mass. And suddenly the numbers work out better. The outer stars can orbit rapidly without escaping, because there is far more mass pulling on them than you can see. The luminous galaxy is like a glowing insect captured in a vast, transparent cocoon whose weight you feel, but whose threads you cannot see. In this picture, when you look at a spiral galaxy, you are not really seeing the galaxy as a whole. You are seeing the part of it that knows how to shine. Our own home, the Milky Way, is no exception. It has the same character of a rotating city of light wrapped inside a much bigger, invisible structure. From our seat, roughly 2/3 of the way out from the center, the Sun orbits the galactic core at a speed of about 220 kilometers every second. In more human terms, that is hundreds of thousands of kilometers every hour. A constant rush around an unseen axis. One full circuit, one galactic year, takes something like between 225 and 250 million Earth years. Since the Earth formed, the solar system has done only a few dozen of these laps. All of recorded human history, every story and empire and quiet life, has unfolded during a small fraction of a single galactic year. While we have been arguing over calendars, our star has barely changed its position on the grand track. We cannot yet rise above the Milky Way to take a direct photograph of its full wheel, but we are slowly building a three-dimensional map from the inside. Missions like Gaia, a spacecraft launched by the European Space Agency, have been measuring the positions, motions, and brightnesses of well over 1 billion stars with exquisite precision. With each new release of data, the static smear of the Milky Way begins to resolve into a dynamic structure. The gentle warp of the outer disk, the tilt of stellar streams, the swirling motions in the bar and spiral arms. We can see, in numbers and maps, how stars slightly closer to the center move relative to those farther out. how clusters are being torn into streams by the galaxy's tides, how the whole disk wobbles as it turns. If you could watch a sped-up movie of this map, with time compressed so that millions of years pass in moments, you would see the Milky Way not as a rigid pinwheel, but as a living, flexing wheel of light, rippled by past collisions and sculpted by the unseen halo of dark matter around it. Our galaxy is not isolated, either. It belongs to that small collection called the local group, and within that family there is another spiral that rivals and slightly exceeds it in size, the Andromeda Galaxy. From a dark site, with clear air and no city lights, you can see Andromeda as a faint, elongated smear in the constellation that bears its name. To the naked eye, it looks unremarkable, a small mist against a black backdrop. Through larger telescopes and sensitive cameras, it reveals itself as another grand spiral, tilted at an angle, its own arms and dust lanes and central bulge visible in delicate detail. That pale blur is not fixed in the sky. Spectroscopic measurements show that Andromeda is moving toward us. Over vast timescales, the Milky Way and Andromeda are on a slow collision course. In roughly 4 to 5 billion years, give or take, the two wheels of light will pass through each other and eventually merge. The word collision conjures images of smashing and shattering. But on the scale of stars, the spaces between are so enormous that direct impacts will be rare. Most stars will simply weave past one another, their orbits radically altered by the combined gravity, while the gas clouds collide more violently, triggering new bursts of star formation. The shapes of both galaxies will stretch into long tidal tails, loops, and bridges. After perhaps another few billion years of rearrangement, the system will settle into a new form, likely a more rounded galaxy, its rotation and structure inherited from the tangled spins of its parents and the dark halos that envelop them. In that future sky, if any eyes are still here to see it from some surviving planet around some surviving star, Andromeda will not be a faint smudge. It will loom huge, its arms crossing much of the heavens, then gradually distorting into a luminous chaos as the two galaxies blend. All of this, the flat rotation curves, the persistence of spiral structures, the looming merger points to the same realization. On galactic scales, rotation is not a superficial detail. It is part of the architecture. Without enough spin, a cloud of proto-galactic gas might have collapsed into a much denser ball. Perhaps an early elliptical galaxy with very different dynamics. With too much spin and not enough mass, the outer regions might have thinned and drifted away. In our case, some balance was struck. Gravity pulled matter inward. Conservation of angular momentum ensured that in falling gas settled into a rotating disk. Dark matter provided enough additional mass spread in a vast halo to keep the spinning stars bound. The visible spiral is a compromise between these elements. The tendency of matter to fall together, the reluctance of rotation to let it collapse straight down, and the deep, unseen reservoir of mass that stiffens the galaxy's grip on its own luminous edges. You are, at this moment, inside one of those wheels of light. Every star you can see on a clear night is a fellow traveler in that rotation, sharing, in a very literal sense, your journey around the galactic center. The constellations we draw are local illusions, patterns picked from a tiny shell of nearby stars. Beyond them, and behind them, is a far larger pattern, the slow circulation of the disk itself, held together by gravity we can see and gravity we cannot. If you could somehow turn off the dark matter, removing the invisible halo in an instant, the outer stars would find themselves moving too quickly for the new, diminished gravity. Over eons, the galaxy would loosen, its outer arms fraying, its bound structure dissolving into a more chaotic cloud of stars. The fact that this is not happening, that the Milky Way has held its shape for most of the universe's history, is an everyday reminder that most of what keeps us bound is not what we can see. The deeper you follow this thought, the stranger it becomes. Rotation here is not just motion. It defines the shapes of structures, determines which forms are stable, sets the stage on which all smaller stories unfold. The wheel is a consequence of initial conditions and physical laws, but once it exists, everything within it is constrained by its turning. And this is still only part of the picture. Up to now, we have been imagining galaxies and stars as objects, moving within a more or less fixed stage, as dancers tracing paths on a floor that does not itself move. Gravity, as Newton once framed it, forces acting at a distance in a static, absolute space. But we have already touched the idea that this stage itself is not rigid. That around a spinning planet, space-time can be slightly dragged along. That around a spinning black hole, the twisting becomes intense, forcing everything nearby to join in the whirl. On the scale of galaxies and their halos, rotation shapes luminous matter through gravity. On the deeper level of general relativity, rotation can also sculpt space-time itself, bending not just where things move, but what straight and still even mean near extreme masses. The next question, then, is not only how the wheels of light hold together, but what happens when rotation becomes so concentrated that it does not just move things through space-time, it stirs the fabric of space-time itself. If even the floor of reality can be twisted, then maybe spinning is not just what things do inside the universe, but something that reaches into the way the universe itself is stitched. For a long time, gravity was pictured as a kind of invisible pull between objects. Two masses see each other across empty space, feel a force, and move accordingly. The Earth pulls on you. You pull back on the Earth. The Sun pulls on the planets. The planets pull on their moons. It is a simple, powerful image. Matter here. Force lines in between. Nothing else. Einstein stepped in and suggested something quieter and stranger. What if there is no force in the old sense at all? What if mass tells space-time how to curve? And curved space-time tells matter how to move. You can imagine space-time as a flexible fabric, not literally a sheet, but as a way to visualize the idea. Place a heavy ball on a stretched cloth, and the cloth dips around it. Smaller marbles rolling nearby no longer follow straight lines. They curve inward, drawn not by an invisible hand, but by the shape of the surface they move on. In Einstein's picture, the heavy ball is a star or a planet. The stretched cloth is space-time. Objects are not being yanked toward the mass. They are simply following the straightest possible paths through a geometry that mass itself has reshaped. Once you accept this, a second thought follows almost naturally. If mass can bend space-time, what happens when that mass spins? Here, the fabric metaphor strains a bit, but it is still useful if you extend it. Instead of just pressing a ball into the sheet, imagine gently twisting the sheet around the ball as well. The surface does not only dip, it swirls. Lines you drew straight before now spiral around. Anything trying to move past the spinning mass finds the very stage beneath it slightly dragged along. This effect is called frame dragging. A reference frame is, loosely, the grid you use to say where and when things happen. Which direction you call forward. Which direction you call east. What you mean by not moving. In everyday life, you pick the Earth as your frame. You say a parked car is still because it shares Earth's general motion. Frame dragging says that near a rotating mass, even these quiet grids begin to twist. The directions themselves are gently pulled around, as if your invisible axes for north and up and still are being wound like threads around a spindle. We have seen hints of this not only in equations, but in orbit. Gravity Probe B, the experiment you heard about before, was built specifically to test these subtle predictions. Engineers created gyroscopes so round and smooth that if they were scaled up to the size of the Earth, the tallest bump would be only a few meters high. They chilled them, shielded them, and set them spinning in a satellite that circled the planet. Each gyroscope's spin axis was pointed in a known direction relative to a distant guide star. If classical gravity were all there was, those axes should have stayed perfectly fixed, like compass needles in empty space. But if space-time around Earth is both curved by its mass and slightly twisted by its rotation, then over time the gyroscope's axes should drift in specific ways. They did. After years of careful measurement and error hunting, the team announced that the tiny changes in the spin directions matched Einstein's predictions. One part of the drift came from the warping of space-time by Earth's mass. Another smaller part came from frame dragging. the planet's rotation literally tugging on the local structure of space-time and making the gyroscopes forward slowly swing. It is a very gentle effect here, almost impossibly small. But it tells you that the idea of rotation is no longer confined to objects moving through a static stage. The stage itself participates. If you want to see what happens when this idea is pushed to an extreme, you look at black holes. A black hole forms when enough mass is compressed into a small enough region that the curvature of space-time around it becomes so severe that even light cannot escape. There is no solid surface, no thing in the ordinary sense. There is an event horizon, a boundary beyond which all paths lead inward and none can return. Most black holes, as far as we can tell, are not just sitting there like frozen pits. They spin. Some of them spin very fast. Near a rapidly rotating black hole, space-time is dragged so fiercely that there are regions where nothing can stand still with respect to distant stars. Even if you fire your rockets and try to hover, the frame you are trying to hold onto is itself being twisted. You are forced to co-rotate with the black hole, carried along in the whirl whether you like it or not. Matter falling towards such an object rarely dives straight in. It forms an accretion disk, a flat, hot, spinning ring of gas and dust spiraling inward. Friction and magnetic fields in that disk heat it to enormous temperatures, making it shine across a range of wavelengths. Closer in, the gas orbits at a significant fraction of the speed of light. Slightly farther out, some of it is redirected into narrow jets that shoot away along the black hole's spin axis, carrying energy and material back into the galaxy. The disk is not a decorative ring. It is a kind of cosmic grinder, where rotation and gravity together shred in falling matter and convert gravitational energy into heat and radiation. For a long time, black holes were mathematical creatures and indirect inferences. We saw stars orbiting invisible masses. We detected X-rays from hot gas near unseen centers. The shapes of some galaxies hinted at hidden monsters in their cores. But we had never simply taken a picture of the environment immediately around an event horizon. On the 10th of April 2019, that changed. The Event Horizon Telescope, a collaboration linking radio observatories across the Earth into a virtual planet-sized dish, released an image of the region around the supermassive black hole at the center of the galaxy Messier 87. It was not a sharp photograph in the usual sense, but a reconstructed view of radio light, bent by intense gravity. In that picture, you see a glowing, uneven ring surrounding a dark central region. The darkness is not the black hole itself, but its shadow, the area where light paths are swallowed or redirected away from us. The bright ring is the inner edge of the accretion flow, where gas circling the hole emits strongly, and its light is magnified and lensed into a kind of halo. You are looking at the consequences of space-time so curved, and likely so dragged by rotation, that light from the far side of the disk is bent over the top and appears above and below the shadow. The ring looks asymmetric because of motion. Gas coming toward us is slightly brightened and compressed in frequency. Gas moving away is dimmed. For the first time, humanity had not just equations or indirect signatures, but a direct visual imprint of what happens when mass and spin carve reality into a whirlpool. A few years earlier, another set of instruments had heard something related. On the 14th of September 2015, the Laser Interferometer Gravitational Wave Observatory LIGO recorded a tiny, transient signal in its twin detectors. It lasted less than a second. It sounded, when converted to audio, like a faint, rising chirp. That delicate noise was not air vibrating. It was space-time. Far away, two black holes had been orbiting each other, losing energy as they spiraled together. As they moved faster and closer, their combined gravitational field changed rapidly, sending ripples outward through space-time itself. When they finally merged into a single, larger spinning hole, the pattern of curvature rang down like a struck bell, releasing a last brief burst of waves. By the time those waves reached Earth, they had stretched and squeezed the distances between LIGO's mirrors by amounts smaller than the width of a proton. And yet, with lasers and meticulous engineering, we were able to measure that stretching, to feel, in a purely physical sense, a distant rotation violently ending and reassembling in the dark. Since that first detection, many more gravitational wave events have been recorded. Black hole mergers, neutron-star collisions, each signal a different pattern of mass and spin spiraling and coiling, and then abruptly changing. The universe has turned out not to be as silent as it looks. It is humming with the vibrations of space-time, a low background music produced by rotating, colliding, collapsing objects everywhere. We stand at an odd moment in history. For most of human existence, the night sky was a picture silent points of light in steady patterns. Then, with radio telescopes, X-ray observatories, gamma-ray detectors, we learned to see that picture in new colors. Now, with gravitational wave observatories, we are beginning to listen to it too. We can hear, in a way, the invisible choreography of rotating masses, feel them tug on the fabric of the universe across unimaginable distances. At this point, the old intuition that there must be some absolute, unmoving background begins to crumble. In everyday life, we cheat by picking convenient frames. You call the floor still, and everything rolling across it moving, even though the floor is on a spinning planet. In orbital mechanics, you sometimes pick the sun as your reference, or the galaxy, and pretend that whatever frame you choose is a kind of neutral stage. But what general relativity insists on is that there is no universal, rigid scaffold underlying everything. Space-time is both the thing being bent and the thing defining what you mean by straight. A massive, spinning object at one location does not just move through that fabric. It reshapes it. It creates a region where not rotating becomes ambiguous, because every possible frame is being twisted. You can still define local frames for convenience. For a given observer, you can pick coordinates that make sense. But there is no global, absolute frame that sits outside all this and stays perfectly still while everything else moves. There is only the network of relationships between masses, motions, and the geometry linking them. Spin, in this deeper view, is not simply something objects do inside space-time, like dancers spinning on a stage. It is something that can reach into the structure of the stage, altering how lines and circles are drawn, how paths connect, how signals propagate. And yet, as strange as all this is, we are still talking about things that you can imagine rotating in some way. Planets, stars, black holes, pairs of massive objects orbiting one another. You can still picture them as whirling lumps of matter, even if the geometry around them is bending and ringing. The concept becomes far less comfortable when you shrink down. At microscopic scales, where quantum mechanics takes over, particles carry a property we still call spin. Electrons, protons, and many other particles have spin in the quantum sense. This spin gives them magnetic moments, affects how they behave in magnetic fields, and shapes the entire architecture of atoms and chemistry. But if you try to imagine an electron as a tiny ball literally spinning in space, you run into trouble. The numbers do not work. To produce the observed magnetic effects by classical spinning, its surface would have to move faster than light. The particle, to the best of our experiments, has no size in the classical sense at all. It behaves as if it were point-like. So what does spin mean when nothing you are allowed to imagine is physically turning? How does rotation exist when there is almost no object to rotate? If, on the scale of galaxies and black holes, spin twists space-time into whirlpools and sends waves humming across the cosmos, then on the scale of electrons, it becomes something more abstract, more deeply built into the rules of reality itself. It is no longer just motion in space. It is a kind of built-in orientation in a space you cannot see. To understand why physicists still use the same word for both, and how that hidden spin shapes everything from magnets to the way matter itself holds together, we have to sink down from the vast, ringing curvature of spacetime to the small, almost unbearable strangeness of the quantum world. If something that small can carry a kind of turning that is not really turning, it makes the familiar idea of spin feel less like motion and more like a hidden rule written into matter itself. Start with the most naive picture. You imagine an electron as a tiny ball. like a grain of dust shrunk down beyond imagining. You know it has a magnetic field, the way a bar magnet does. You also know that when electrons sit in atoms, that magnetism helps explain why spectral lines split into multiple closely spaced colors in a magnetic field. The simple, almost irresistible thought is, maybe the electron is literally spinning, like a minuscule charged sphere. Its rotation would create a circulating current, and that current would generate a magnetic field. Then you put numbers into that picture and it collapses. To match the measured magnetic moment of the electron, that hypothetical little ball would have to spin so fast that points on its surface would need to move faster than light. Faster than the universe allows anything with mass to move. The stresses in such a spinning object would be absurd. Even if you ignore relativity and just use old classical mechanics, the required energies make no physical sense. The tiny ball would tear itself apart. And yet, when you measure how electrons behave in magnetic fields, in atoms, in beams, they act as though they carry an internal angular momentum, a built-in directional quantity with a definite magnitude. They precess in fields like gyroscopes. They produce magnetic effects in ways that look suspiciously like the behavior of spinning charged objects. This was the puzzle that two young physicists, George Uhlenbeck and Samuel Goudsmit, walked into in the year 1925. They were trying to make sense of fine details in atomic spectra. When you heat a gas and look at its light through a prism or a spectrograph, you see bright lines at specific colors. These lines come from electrons jumping between allowed energy levels in atoms. But when people measured those lines carefully, they noticed that some of them were split into doublets, two closely spaced lines where simple theory predicted only one. To account for this, Uhlenbeck and Goudsmit proposed that the electron has an additional quantum property, a kind of intrinsic angular momentum they called spin. Not spin in the old mechanical sense, but something that would add an extra degree of freedom. In their picture, an electron in a given orbital could be in one of two internal states, which you might label up or down, and that would affect its energy in a magnetic field, splitting spectral lines. The idea was bold, and, at first, not universally welcomed. Some senior physicists pointed out the same problem you just saw. If you think of this literally as a spinning ball, the speeds make no sense. The classical picture simply does not fit reality. There were worries that the proposal was just a patched-on fix, but quantum theory itself was in the middle of a revolution. Over the next few years, as the mathematics of wave functions and operators and symmetries solidified, spin was absorbed into the framework in a more rigorous way. It turned out that when you consider how particles behave under rotations in quantum mechanics, there are natural representations that behave like objects with half a unit of angular momentum. You do not need a literal spinning surface. The electron's spin emerges as an intrinsic label, a built-in property tied to the deep symmetries of space. In that mature view, spin is not something the electron does. It is something the electron is. You can think of it as an extra line in the particle's identity file. Along with charge and mass, an electron has spin, a fixed magnitude, and an orientation that can point in different directions relative to an external field. Because of that, it behaves like a tiny magnet. Place a collection of electrons in a magnetic field, and their spins tend to align or anti-align, causing energy shifts that show up in experiments. This tiny internal arrow turns out to be essential for the structure of matter. Wolfgang Pauli introduced what is now called the exclusion principle. No two electrons in an atom can share the exact same quantum state. If you think of an atomic orbital as a kind of standing wave around the nucleus, with a certain energy and shape, you might naively try to pack as many electrons into it as you like. The exclusion principle says, no, for a given orbital, you may have at most two electrons, and only if their spins are opposite, one up and one down. That single rule ripples outward into the entire periodic table. Electrons fill up available orbitals in atoms in a very particular order. The first shell around the nucleus fills with two electrons, their spins paired. The next shells can hold more. with different shapes and energies, but always under the constraint that each distinct state holds at most 2 electrons with opposite spin. As you go from hydrogen with 1 electron to helium with 2 to lithium with 3 and on, you are essentially watching spin-governed slots being filled. The pattern in which those slots fill determines the chemical behavior of each element. Atoms with full outer shells tend to be inert. Atoms, 1 electron short or 1 electron over, tend to be reactive, eager to lose or gain to reach a more stable configuration. The rows and columns of the periodic table, with their repeating groups and families, emerge from the way spin and exclusion sculpt electron configurations. Without spin, and without Pauli's principle, electrons would all sink into the lowest energy levels. There would be no shell structure. All atoms would look distressingly similar. Chemistry as you know it, bonds, molecules, materials, would not exist in anything like its present form. Matter might be a kind of undifferentiated superatom, or collapse into denser states. The familiar solidity and variety of the world rests on this invisible bookkeeping rule about spin states. Spin is not just a theoretical curiosity. It underpins technologies you encounter without thinking about it. When you slide a magnet across your refrigerator door and it sticks, you are feeling the collective effect of unpaired electron spins in the atoms of the magnet. In many magnetic materials, electron spins tend to align in regions, their tiny magnetic moments reinforcing one another. Large patches of aligned spin give rise to macroscopic magnetism, capable of lifting paper, holding notes, guiding compass needles. Traditional magnetic storage, old cassette tapes, hard drives with spinning disks, relied on the orientation of these magnetic domains to encode bits. One direction of local magnetization stood for a 1, the opposite direction for a 0. Reading and writing data meant flipping spin alignments in microscopic regions. More recent devices explore a field called spintronics, where the spin of electrons, not just their charge, is used to store and manipulate information. There are experimental memories where a bit is represented by the spin state in a tiny magnetic tunnel junction, switching between configurations with different resistance. Underneath the engineering, it is still that same quantum spin, an internal orientation that only takes certain discrete options, doing the work. In medical imaging, spin shows up in a more intimate way. If you have ever been inside an MRI scanner, lying on your back while the machine thumps and hums around you, you have been part of a spin experiment. The human body is full of hydrogen nuclei, each one a proton with its own spin. In the scanner's strong magnetic field, those nuclear spins tend to align slightly with the field, like a vast number of tiny compasses. Radio waves are then used to tip those spins away from alignment. As they relax back, they precess and emit signals that can be picked up by coils. Different tissues in your body cause those spins to behave differently, changing how quickly they return to equilibrium and how strong the signals are. By mapping these responses across space, the machine constructs detailed images of your insides. The quiet fact is that the picture is built from the whisper of spinning nuclei returning to alignment. Even the device you might be using right now to listen to this, or to read these words, is quietly full of spin effects. Semiconductors are designed using quantum rules that include spin. The behavior of electrons in transistors, the way they move through materials, is influenced by spin-orbit coupling and band structures that emerge from electron statistics. Sensors that detect orientation, magnetic fields, and currents often exploit spin-related phenomena. You are holding, or sitting near, a forest of controlled spins, silent, microscopic gyroscopes, and magnets working together to make a digital world feel solid and responsive. Step back, and the word begins to echo. Spin of electrons, spin of atomic nuclei, spin of neutron stars and pulsars, spin of planets and stars, spin of galaxies and black holes. At every scale, from the smallest building blocks of matter up to the largest luminous structures in the universe, the language of spin and rotation keeps returning. Part of that recurrence is habit. Humans like to reuse words when they notice patterns. Quantum spin is not the same as a basketball rotating through the air. A galaxy's rotation curve is not governed by the same simple formulas that describe a toy top. It is easy to forget that we are using one syllable to cover many different kinds of structure, but part of it hints at something deeper. Conservation of angular momentum, the tendency for spinning motion to persist unless acted upon, is one of the most fundamental symmetries in physics. At the quantum level, spin arises from the way particles transform under rotations. From the deep fact that turning the world around an axis should not change the underlying laws. At the cosmic level, the same conservation helps explain why collapsing clouds spin up and why galaxies keep turning unless torqued. The language is not just poetry. It is pointing at a family of related ideas: orientation, symmetry, persistence of rotational motion, the way the universe responds when you try to twist it. Somewhere between metaphor and mathematics, spin has become a thread that ties together the behavior of the very small and the very large. It is not that electrons and galaxies share some mystical spinning essence. It is that the same abstract structures, symmetries, conservation laws, geometric constraints show up again and again, written in different alphabets. We began on a bed, feeling nothing of Earth's rotation. We stepped out to spinning planets, stars, and galaxies. We dove down to black holes, dragging space-time and particles whose spin is an intrinsic quantum label rather than a literal whirl. Everywhere, something that looks like turning appears, which raises a last, unsettling question. If spin is so woven into the behavior of matter and space-time at every scale we have managed to probe, what about the whole thing? Is the universe itself just a sum of local spins, all of them cancelling out in different directions? Or could there be, buried in the background radiation and the large-scale structure of galaxies, a trace of a grander rotation, a slow, almost imperceptible turning of the cosmos as a whole? If the universe does carry some hidden turning, you would not see it by watching a single star or galaxy. You would have to step back so far that everything you know becomes one pattern on a single canvas. The extreme thought experiment goes like this. What if the entire universe were rotating as one? Not just clouds collapsing, not just galaxies wheeling within space, but space-time itself turning around some immense axis. If that were true, you would expect to see traces of it written into the sky. Some directions might be special. Light might behave differently along one axis than another. On the very largest scales, where randomness should smooth things out, you might find a faint, stubborn swirl. To look for something like that, you need a background that comes from everywhere at once. Not the light of stars, which is local and late, but the oldest light we can see, the cosmic microwave background. The universe once was much hotter and denser than it is now. In its early moments, matter and radiation were so tightly coupled that space was filled with a glowing, opaque plasma. Photons bounced constantly off free electrons, never traveling far. As the cosmos expanded, it cooled. After a few 100,000 years, temperatures fell enough for protons and electrons to combine into neutral atoms. Suddenly, light could travel freely. The fog thinned. Photons released at that time have been streaming through space ever since, stretched by cosmic expansion into microwaves. We see that ancient light today as a nearly uniform glow across the sky, with a temperature of about 2 7/10 Kelvin, just a few degrees above absolute zero. It is the universe's baby picture, a snapshot of conditions when it was roughly 380,000 years old. If the cosmos has a preferred axis, a large-scale spin, it should be whispered into that picture. The pattern of tiny hot and cold spots in the microwave background carries information about density fluctuations, sound waves in the early plasma, and the overall geometry of space-time. It also serves as a test of isotropy. Does the universe look the same in every direction, or is there some grand alignment? The story of how we found this background light is almost comically down to earth. In the mid-1960s, two radio astronomers, Arno Penzias and Robert Wilson, were using a large horn-shaped microwave antenna in New Jersey, originally built for satellite communication experiments. They kept encountering a persistent hiss in their measurements. It came from every direction, day and night. They checked their equipment. They accounted for known sources of interference. The noise would not go away. At one point, suspecting something more mundane, they climbed into the antenna and found pigeons roosting inside, along with a generous layer of droppings. They cleaned the mess, gently evicted the birds, and tried again. The hiss remained. Whatever was producing the signal was not local. It was not the instrument. It was not the pigeons. It was something else. Around the same time, other physicists had predicted that if the universe began in a hot, dense state and expanded, there should be a leftover glow, a relic radiation cooled into microwaves. Penzias and Wilson's stubborn noise turned out to be exactly that. The fossil light of the early cosmos, arriving from all directions. What had looked, at first, like an annoying background, became one of the most important discoveries in cosmology. At first, the cosmic microwave background seemed beautifully smooth. The same temperature everywhere. Within a tiny fraction of a degree, that uniformity was a triumph for the cosmological principle. The idea that on large enough scales the universe is homogeneous and isotropic, no preferred places, no preferred directions. But to understand cosmic structure, scientists needed more than smoothness. They needed to find tiny variations, imprints of the initial lumps and waves that would later grow into galaxies and clusters. They also needed to test whether the apparent isotropy really held up under closer inspection. In the early 1990s, a satellite called COBE, the Cosmic Background Explorer, mapped the microwave background with enough precision to reveal small anisotropies, slight hot and cold spots scattered across the sky. These fluctuations were incredibly subtle, but they were there, a mottled texture on the otherwise uniform canvas. The result confirmed key predictions of the Big Bang model and showed that the early universe was not perfectly smooth, just very nearly so. Later, missions sharpened that view. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, provided a much higher resolution map, measuring the temperature variations across the full sky with fine detail. Then, in 2009, the Planck satellite took the work further, refining the measurements and adding polarization data, which encodes information about the direction of the electric field of the radiation and carries clues about scattering in the early universe. With these maps, cosmologists could test rotating universe models in a serious way. If space-time as a whole were spinning, or if there were a global preferred direction imprinted at large scales, you would expect the microwave background to show specific patterns. Certain kinds of asymmetry, correlations between distant regions, polarization signatures that line up along some axis. Analyses based on WMAP and Planck data have placed very strong limits on any such global rotation. Within the sensitivity of our instruments, the universe appears remarkably isotropic. You can describe the expansion with the same Hubble parameter in all directions to an incredible degree of accuracy. Any large-scale vorticity, the technical term for global spin, is constrained to be so tiny compared to the overall expansion that, for all practical purposes, the universe does not seem to be rotating as one rigid object. That is the conservative conclusion. No evidence for a global spin. Tightly bounded possibilities for any anisotropic background rotation. But the story refused to be entirely clean. When researchers examined the largest angular scales in the WMAP data, the pattern of fluctuations spanning huge patches of sky, they noticed odd alignments. Certain low-order multipoles, the broadest features in the temperature map, seemed to line up with each other in a way that was statistically unexpected, as if some preferred plane or axis was threading through them. There was also a mild hemispheric asymmetry. One half of the sky appeared to have slightly stronger fluctuations than the other. In 2005, this collection of anomalies acquired a dramatic nickname: the Axis of Evil. The phrase reflected both the discomfort and the mischief of the moment. If real, such alignments could hint at a breakdown of the cosmological principle, a suggestion that the universe has a built-in directional structure on scales where everything was supposed to be random and uniform. If spurious, they were just the kind of pattern-seeking behavior humans are prone to in noisy data. Planck's later, more precise maps found similar features. The alignments did not vanish with better data, which made them harder to dismiss outright. At the same time, their statistical significance remained modest, sensitive to how you processed the sky, how you removed foreground emissions from our own galaxy, which parts of the map you masked. Some analyses suggested that contamination from dust and synchrotron radiation or subtle processing choices could create or enhance such patterns. Faced with this, the community's response has been cautious. Most cosmologists treat the axis of evil as an intriguing but unresolved quirk. It could be a hint of new physics, perhaps related to unusual initial conditions, topological features, or remnants of pre-inflationary structure. It could be a sign that our methods for cleaning the data are not perfect, that the galaxy's own emissions are trickier than we thought. Or it could simply be a statistical fluke. In a vast dataset, unlikely alignments occasionally happen by chance, and we naturally focus on the surprising ones. What it is not, so far, is compelling evidence that the universe is spinning as a single solid. Rotating universe models tested against the full range of CMB data and other cosmological observations generally fare poorly. They tend to conflict with the observed isotropy, with the pattern of acoustic peaks in the power spectrum, with polarization measurements. The elegant, nearly isotropic universe of standard cosmology, expanding but not globally twisting, continues to fit the bulk of the evidence astonishingly well. In that sense, the extreme vision of a cosmos with a single, grand spin axis seems to be ruled out, or at least squeezed into very narrow, almost irrelevant possibilities. If there is any overall rotation, it is so small compared to the expansion that it barely leaves a mark. Yet the very act of asking the question has deepened our understanding. It forced us to look closely at how we know the universe is isotropic, to quantify that knowledge, to chase down every possible source of error. It made us confront our own patterned craving minds, which love to draw meaning from clumps and lines. And it left us with an odd juxtaposition. On the largest scales we can measure, the universe behaves as if it has no preferred direction. Its baby picture looks the same in every orientation, aside from small fluctuations that match the predictions of simple, non-rotating models. There is no obvious cosmic arrow painted across the sky, no clear sign that everything is turning around a single axis, like a gigantic Ferris wheel. On smaller scales, the story is different. Galaxies spin, clusters rotate, clouds swirl, stars twirl and fling off material. Black holes drag spacetime into whirlpools. Planets roll around their stars. Particles carry quantum spin that shapes chemistry and technology. Everywhere we look, from the innards of atoms to the hearts of galaxies, we find local whirlpools, smaller or larger eddies in a sea that, statistically, has no dominant swirl. The universe, it seems, is not a single spinning coin, but a storm of coins tossed in every direction, their flips and rotations mostly cancelling out when you average over enough of them. If you wanted to be poetic, you could say that reality has chosen distributed spin over monolithic spin. Instead of a cosmos rotating as one, it has built itself from countless small turnings, each one carrying its own story, its own consequences. Some of those stories are almost too slow for us to notice. A galaxy taking hundreds of millions of years to complete a single turn. Others are so extreme that they send waves through space-time, and some are so precise and regular that they can serve as clocks. Because if you zoom in not to the smallest scales, but to the dense, compact remnants of stars, you find objects whose rotations are so measured, so steady, that they can outdo our best mechanical timepieces. They are where the universe's habit of spinning becomes a kind of heartbeat. Rapid, relentless, and astonishingly trustworthy. Those heartbeats are not mechanical. They are not ticking gears or vibrating quartz. They are whole stars, crushed and spinning, marking out seconds and centuries with a patience that makes human clocks feel fragile. A neutron star begins its life in violence. Take a star much more massive than the Sunday. Let it burn for millions of years, fusing lighter elements into heavier ones in its core, building up layers like an onion. Eventually, The fusion that holds up the star against its own gravity can no longer continue. The core cannot support itself. In a fraction of a second, the inner regions collapse inward, the outer layers rebound, and a supernova tears the star apart. What is left behind at the center, if conditions are right, is a neutron star, an object only a few tens of kilometers across, yet with more mass than our sun squeezed into that tiny volume. Imagine compressing a mountain to the size of a sugar cube, then keep going. The material inside is so dense that atoms themselves have been crushed. Electrons and protons have been forced together into neutrons. The result is a gigantic atomic nucleus, a sphere of neutron-rich matter with a crust, a core, magnetic fields, and a spin. That spin is the ghost of the original star's rotation, amplified by collapse. When the star was huge, its outer layers could slowly turn without much drama. When that mass is squeezed into a space the size of a city, conservation of angular momentum demands that the rotation rate skyrocket. The same way a skater speeds up by pulling in her arms, the star speeds up by pulling all its matter closer to its spin axis. Newborn neutron stars can spin many times each second. Some whirl dozens of times in that short interval. Others, called millisecond pulsars, can complete hundreds of rotations each second. From the surface of such a star, a point on the equator is racing around at a significant fraction of the speed of light. Surround that spinning mass with an intense magnetic field, and something even more spectacular happens. Charged particles near the star are guided along magnetic field lines, accelerated, and hurled out in beams from the magnetic poles. These beams can emit strongly in radio waves, X-rays, and other parts of the spectrum. If the star's magnetic axis is tilted relative to its rotation axis, those beams sweep through space like the beams from a lighthouse. Most of the time, they miss us completely. But if Earth happens to lie in the path of one of those sweeping cones, then each rotation brings a flash. To our radio telescopes, the neutron star announces its spin with regular pulses of radiation, like a tiny cosmic metronome beating time in the dark. We call such objects pulsars. The first one was noticed not by a senior professor, but by a graduate student, carefully checking a long stream of data. In the summer of 1967, Jocelyn Bell, working at the University of Cambridge, was in charge of monitoring the output from a new radio telescope array built to study the scintillation of distant radio sources. The instrument produced long rolls of chart paper covered with squiggly lines, each line a record of signal strength over time. It was repetitive, tedious work to scan them. But buried in all that noise, she spotted something odd, a series of small, sharp scratches that repeated with uncanny regularity. At first, she was not sure what to make of them. They were narrow. They did not follow the pattern of known interference, and they reappeared in the same part of the sky. On the 28th of November, 1967, she confirmed that the pulses were repeating with a period of about 1 1/3 seconds, with a stability that seemed almost unnatural. The team jokingly labeled the source LGM1 for Little Green Men 1, a tongue-in-cheek nod to the idea that perhaps they had stumbled on a beacon from an alien civilization. The more they looked, the less that idea held. Soon, similar pulsing sources were found in other locations, with different periods. The pattern began to look like a new class of astronomical object rather than a deliberate signal. The theoretical interpretation followed. Rapidly spinning, highly magnetized neutron stars, their beams sweeping past Earth with each rotation. Once you know what to listen for, the universe reveals more of them. Thousands of pulsars have been catalogued since that first discovery. They are scattered through our galaxy, especially concentrated in regions with old supernova remnants and dense stellar populations, like globular clusters. Some of them are in binary systems, locked in tight orbits with companion stars or other neutron stars. These pairs have become laboratories for testing general relativity. As they orbit, they lose energy to gravitational radiation, slowly spiraling together. Careful timing of their pulses has provided indirect evidence for gravitational waves long before instruments like LIGO directly detected those ripples in spacetime. Others, The millisecond pulsars are astonishingly precise. Over long periods, the intervals between their pulses can be predicted with a regularity that rivals, and in some cases surpasses, the best human timekeeping devices. They are natural rotation counters, their spin slowed only very gradually by magnetic braking and the emission of radiation. Astronomers sometimes turn radio observations into sound by assigning each pulse a click in an audio track. When you listen to such a recording, the abstract nature of these objects becomes strangely tangible. Some pulsars tick slowly. Click, click, click. Each one a rotation of a star no larger than a city. Others, spinning hundreds of times each second, become a steady buzz, a tone that your ear hears as continuous, even though it is made of discrete beats. It is almost impossible not to imagine them as hearts, somewhere out there, in the direction of a familiar constellation. A tiny, dense star spins and taps time into the dark, indifferent to whether anyone is listening. The remarkable thing is how trustworthy these taps are. Apart from occasional glitches, sudden, tiny jumps in rotation rate, thought to be caused by shifts in the neutron star's interior pulsars, behave like clocks. When we see their pulses arrive a bit early or late, we can interpret that change as a sign of motion between us and them. Earth's orbit, the tug of a companion, the influence of gravitational waves passing through. In fact, there are projects that use networks of millisecond pulsars spread across the sky as a kind of galactic-scale gravitational wave detector. By monitoring the arrival times of pulses from many such stars, researchers hope to see correlated deviations that would signal space-time ripples from supermassive black hole binaries and other enormous events. In that vision, the galaxy becomes an observatory, and pulsars are its synchronized detectors. For our purposes, they are also a testament to how consistent the laws of physics seem to be. A neutron star in some distant spiral arm, formed billions of years ago, follows rules we can write down in equations here and now. Its rotation slows in ways we can model. Its magnetic fields evolve and interact with surrounding plasma in ways that, while complex, still obey the same Maxwell and Einstein equations we test in laboratories. If suddenly, without cause, pulsars across the sky began to drift unpredictably, their pulses wandering in ways that no theory could accommodate, it would be more than an astronomical oddity. It would shake the foundation of our trust that the universe is governed by coherent principles. Instead, they keep turning. They keep counting. There is a kind of comfort in that. Human timekeeping is full of failure modes. Batteries die, springs unwind, electronics glitch. Our clocks are careful contraptions, fighting entropy. Pulsars are expressions of it. They are what happens when gravity and collapse and rotation settle into a temporary equilibrium. Their constancy is not imposed from outside. It emerges from the way matter behaves under extreme conditions. The universe, in other words, has been using rotating objects to keep rhythm long before we learned to do the same with pendulums and quartz crystals and atomic transitions. That parallel is hard to ignore. Somewhere between a neutron star ticking away in a dark corner of the Milky Way and the gyroscope in your phone, a line connects. Rotation harnessed as a measure, a stabilizer, a reference. Nature uses spin to track time and structure space. Humans, decades into the age of technology, have learned to mimic that trick on far smaller, more fragile scales. Long before anyone wrote equations about angular momentum, there was a small hand, a wooden floor, and a toy that refused to fall over. A child winds up a spinning top and lets it drop. For a brief moment, it stutters, catches, and then something clicks into place. The top straightens. It stands almost proudly on its narrow tip, humming in a tiny circle. As long as it spins fast, it holds itself upright against gravity. Then, almost imperceptibly, the sound changes. The rotation slows. A wobble appears. At first gentle, then wild. The top staggers and finally collapses onto its side, skittering a little before coming to rest. You do not need vocabulary to read that scene. Fast, spin, stable, slow spin, wobble, no spin, fall. That is rotational inertia, written in wood and paint. Adults like to dress it up with language. They talk about angular momentum and torque and precession, but the child just sees a thing that stays standing only as long as it keeps turning. Some part of the brain quietly notes the rule. Spinning makes things stubborn. Take that spin away, and they surrender to the pull of the world. That simple observation follows us into more serious places. In the 19th and 20th centuries, as ships began to cross oceans without always seeing the shore, and aircraft learned to climb into clouds where nothing outside the window could be trusted, people needed a way to know which way they were pointing when their bodies could no longer tell them. Enter the classical gyroscope. Picture a heavy metal wheel mounted inside a set of rings that allow it to pivot freely in any direction. Spin the wheel up to a high speed, and its axis suddenly behaves like the spinning tops. It becomes resistant to being turned. Try to tilt it, and you feel a sideways push. Try to twist the frame, and the spinning mass fights back, insisting on keeping its orientation relative to distant space. Engineers learned to cage these spinning wheels in clever housings, to mount them in gimbals that allowed motion in all three dimensions, and to connect them to dials and indicators. A gyroscope in a submarine could hold the ship's sense of heading even when no stars were visible and magnetic compasses were unreliable. A gyroscope in an aircraft's attitude indicator could show the pilot where level was even in a violent bank. Modern inertial navigation systems evolved from these devices, combining multiple gyros and accelerometers to track motion without outside references. The principle remains the same. Use something that resists changes in its rotation to measure everything else. Over time, the hardware shrank. Big spinning wheels in vacuum housings gave way to ring lasers and fiber optic loops, where light itself plays the role of the moving mass. Then, with the rise of microfabrication, the gyroscope took another leap. It became a tiny vibrating structure etched onto a chip, hardly larger than a grain of sand. These miniature sensors, microelectromechanical systems, or MEMS, live inside almost every smartphone. When you tilt your phone from portrait to landscape and the screen obediently rotates, it is because little mechanical elements inside are vibrating and feeling the Coriolis forces produced by your hand's motion. When a racing game lets you steer by leaning the device left and right, it is those same sensors translating your rotations into digital signals. When camera stabilization smooths out your shaky footsteps, software is using the measured motion to counter-rotate its view. Your pocket carries a tiny echo of the old ship's gyroscope, a spinning top so small you never see it, constantly reporting on how the device is being turned. In combination with accelerometers, it gives your phone a sense of balance, a way to feel motion rather than just see or hear it. If you put that next to Foucault's pendulum in your mind, the rhyme is obvious. The pendulum, hanging in a great cathedral or museum, reveals Earth's spin by stubbornly keeping its swing plane fixed while the floor turns beneath it. It lets your eyes see that the ground is rotating. The gyro in your phone, whispering its data into circuits, lets the device feel your hand's rotation, even when your eyes cannot see the small twists. Same theme. Use something with rotational inertia to detect motion that would otherwise melt into the background. One is monumental steel and marble, the other is silicon and code. Both are negotiations with spin. In some environments, trusting such instruments is not just convenient. It is a matter of survival. Pilots learn early that the human body is a poor judge of rotation when visual cues are missing. In clouds or at night over a dark ocean, the inner ear can be tricked. A long, gentle turn can feel like straight flight. A return to straight and level can feel like a turn in the opposite direction. The sense of up and down can drift without you noticing. That is why instrument flight training is, in part, a lesson in humility. You sit under a hood that blocks your view outside and fly only by reference to the gauges. Your body tells you one story. The attitude indicator and turn coordinator tell you another. If you are unlucky and you believe your body, you can enter a spiral or a stall while feeling with eerie conviction that you are flying straight and safe. Many accidents have this pattern. Pilots who, in poor visibility, begin to argue with the instruments, trying to reconcile their feeling with the readings, and choosing the feeling. The result is often tragic. The corrective wisdom sounds almost philosophical. When your senses are misled, trust the thing that is tied more directly to the physics. Trust the gyros, trust the data. Rotation, in that context, is not just a phenomenon to admire in the sky. It is an adversary and an ally. It can fool you, and it can save you, depending on how you hold it. Stories, notice this. Think of the spinning top in the film Inception from the year 2010. It is a small object, a pocket toy, but inside the story it becomes a totem. The one thing that behaves differently in dreams than in waking life. In the dream world, the top spins forever, refusing to wobble or fall. In reality, it eventually loses speed and tips over. The entire ending of the film hangs on a single image. The top spinning on a table, starting to wobble. Then the cut to black before we see whether it falls. Viewers argued endlessly over that cut. Did it topple? Did it not? Is the character still dreaming? A tiny rotating object becomes a symbol for the boundary between illusion and reality, stable and unstable, the place where you cannot quite trust your own perception. It is not an accident that the filmmakers chose a spinning top instead of, say, a coin or a die. Somewhere in us, we associate sustained, impossible rotation with unreality, and the loss of rotation with waking up. Foucault's Pendulum tells us the world is turning. The totem in Inception suggests that a world in which a top never falls might be one level too deep. Science fiction returns to rotation whenever it wants to talk about artificial gravity as well. In 2001, A Space Odyssey, the great wheel-shaped station spins in the vacuum. Astronauts stroll along its inner surface as if under normal gravity, their feet pointing outward. The rotation supplies the centrifugal effect that presses them against the floor. The film does not belabor the physics. It simply lets you see people walking in a circle in space and invites your body to accept the illusion. This could feel like home. Later stories imagine larger and more elaborate versions. Ring habitats, cylinders many kilometers long, entire communities living on the inside of rotating drums. The details of engineering such things are brutal. Materials must withstand enormous stresses. Attitude and stability must be maintained. But the idea persists in our imagination because it is one of the few straightforward ways to simulate weight in orbit. Spin something big enough, and the outward push can stand in for the downward pull we evolved with. In all these uses, tops, gyros, pendulums, spinning stations, rotation stops being just a background fact about planets. It becomes a tool. We measure time with it, whether by the sweep of a neutron star's beam or the steady swing of a pendulum clock. We stabilize vehicles with it, from bicycles to submarines to rockets. We orient ourselves in 3 dimensions with it, via gyroscopic sensors that feel our turns more honestly than our ears do. We tell stories with it, encoding anxieties about what is real and what is not into the fate of a wobbling totem. You could say that, in learning to harness rotation, we have found a way to borrow the universe's own habits. Out there, stars collapse and spin. Galaxies wheel slowly. Black holes drag frames around and send ripples through space-time. In here, in our pockets and on our desks and in our machines, small spinning and vibrating things keep our pictures upright, our planes level, our data aligned, our stories coherent. It is easy to forget that this is a fairly recent skill. For most of human history, we looked up and saw a firm dome of stars turning around a still Earth. The idea that the ground could be moving was absurd, even offensive. The sky moved. We did not. Only gradually, over centuries, did that picture flip. We went from being the quiet center around which the heavens wheeled to being riders on a rotating world, circling a star in a galaxy that is itself in motion. What now feels obvious, that the floor is not as still as it seems, was once a shocking inversion. And even now, knowing what we know, our bodies still default to the old story. They insist the ground is fixed and the sky moves. Every time a toy top stands upright on the floor, every time a pendulum traces out Earth's rotation, every time a gyro tells us our sense of balance is lying, we are reminded gently that what feels still is often only a temporary agreement between our nerves and a moving world. For most of our history, we did not even know there was an agreement. The body said the floor was still, the sky was moving, and for a very long time almost no one thought to argue with that. If you step into the mind of someone thousands of years ago, the universe is surprisingly simple. Above you, a dome of stars turns in an orderly way. The sun rises in the east, climbs and sinks in the west. The moon waxes and wanes, wandering among the constellations. Planets trace strange loops against the background, but they do it on that same celestial stage. What moves is obvious, the lights overhead. What does not move is equally obvious, the earth under your feet. You can stamp on it, build on it, sleep on it, and it does not sway or hum. It feels like the one solid reference in a restless sky. From that experience, whole models grew. Philosophers and astronomers built pictures in which Earth sat at the center, unmoving, while concentric crystalline spheres carried the moon, sun, planets, and stars around it. It was not just a practical model. It fit the sense of importance humans placed on themselves. The heavens revolved around us. Quite literally, our world was the axle. For millennia, that view felt not only true but inevitable. To suggest the opposite, that Earth might be moving and the sky might be more or less still, would have sounded like claiming that the floor of your house slides silently while the furniture hovers. It was technically possible to imagine, but utterly alien to intuition. It took small cracks in that certainty to open the way. In the 16th century, Copernicus quietly proposed a different arrangement. Put the sun at the center. Let Earth and the other planets orbit it. And many of the sky's complicated motions become simpler. Retrograde loops of planets like Mars fall out naturally as a side effect of Earth's own motion. His model was not perfect. It still used circular orbits and added epicycles to match observations. But it shifted the emotional frame. Suddenly, Earth was one wanderer, among others, not the fixed pivot. A generation later, Johannes Kepler refined the picture by abandoning perfect circles. He found that planets move in ellipses with the sun at one focus, speeding up when they are closer in and slowing down when they are farther away. The orbits became more faithful to reality and less flattering to human longing for symmetry. Then, in the early 17th century, Galileo turned a small telescope to the sky and saw something that the old models struggled to swallow. Around Jupiter, he watched tiny points of light change position night after night. They were not fixed stars. They were moons, clearly orbiting Jupiter itself. Here was a miniature version of the Copernican insult written plainly in the sky. Not everything goes around Earth. Other centers exist. Other systems spin. Each of these steps chipped away at the idea that the universe revolves around us. But for a long time, even after heliocentrism gained ground, the shift remained mostly a matter of diagrams and calculations. You could accept that Earth moved around the sun without ever feeling it. The ground was still too quiet. It was not until the middle of the 19th century that someone gave the public a way to watch Earth's rotation unfold, slowly, in a building they could walk into. Léon Foucault's pendulum in the Panthéon in Paris did not shout. It swung. Back and forth, while the floor under it imperceptibly turned with the planet. Over hours, the plane of the pendulum's motion appeared to rotate, knocking over little markers arranged in a circle. The message was patient. You are on a spinning world, and you can see it if you are willing to sit still and let time do the talking. People lined up to watch. Some walked away unsettled. The pendulum did not argue, it just kept going. Even then, the broader cosmos was imagined as fairly static. Stars might move slowly. The Milky Way might be a fixed backdrop. Gravity, in Newton's formulation, was a force acting in an otherwise unchanging space. Time flowed on, but the stage was, in some sense, permanent. The 20th century shattered that, gently at first, then completely. Astronomers like Vesto, Slipher, and Edwin Hubble measured the spectra of distant nebulae and noticed that many of them were redshifted, their light stretched toward longer wavelengths. Interpreted as a Doppler effect, it meant those galaxies were receding from us. The farther away, the greater the redshift. In Hubble's famous plot, distance and recession speed lined up in a roughly straight line. Space itself, it seemed, was expanding. Galaxies were not simply flying through a static void. The distances between them were growing as the fabric of the universe stretched. The picture of a still universe faded. We began to live, at least in theory, in a cosmos with a history, denser and hotter in the past, expanding and cooling over billions of years. Even the vacuum was no longer just emptiness. It had geometry. It could bend and evolve. Later observations would suggest it might even have a kind of built-in energy that accelerates expansion. Then general relativity entered, with its curved space-time and frame dragging, turning gravity from a force into geometry. The stage was not only bending under mass, it was responsive, malleable, dynamic. The idea that there could be a truly unchanging, eternal, perfectly still universe began to look more like a comforting dream than a viable model. In that context, the event in September 2015 was not just a technical achievement. It was a kind of emotional punctuation. On the 14th of September 2015, LIGO's detectors felt the tiny stretch and squeeze of spacetime as two black holes far away spiraled together and merged. For a fleeting moment, the distance between mirrors on Earth changed by a fraction of a proton's width as a gravitational wave washed through. That signal was the first direct evidence that spacetime can ripple, that catastrophic rotations and collisions elsewhere send vibrations through the cosmos that we can measure here. It anchored the notion of a dynamic universe not just in images or redshifts, but in the physical stretching of the distances around us. By then, the old story of a still, eternal cosmos had been replaced several times over. Geocentrism gave way to heliocentrism. The notion of a static, perfectly balanced universe yielded to an expanding one. The idea of gravity as a simple, invisible pull was replaced by curved spacetime. Finally, even spacetime lost its quiet, revealed as something that can be stirred by spinning masses and made to ring. Every one of those shifts came with human resistance. It is easy, from a distance, to present them as neat progressions in a textbook: old model, anomaly, new theory, acceptance. Lived from the inside, they were messy. They threatened identities, theologies, philosophies. If Earth was not the center, what did that say about humans? If the universe had a beginning, what did that mean for ideas of eternity? If spacetime itself could change, where was the solid ground for metaphysics? People argued, sometimes with data, sometimes with fear. Some lost positions, some recanted, some refused. Over generations, what once seemed unbearable became obvious, and new certainties grew in place of the old ones. You can feel something similar, in smaller ways, in your own life. There are periods when everything feels fixed. Your routines, your relationships, your sense of who you are, they become the still earth under a moving sky. Then something happens. A job ends. A person leaves. A diagnosis arrives. A belief cracks. Suddenly, what you thought was the floor reveals itself as one more moving piece. The first reaction is often vertigo, a feeling that you have been betrayed by your senses, by your understanding. You did not feel the slow changes building up, the pressures accumulating, the tiny spins amplifying, and now the pendulum is in front of you, knocking over markers, showing you that the room was always turning. If you only ever trusted the feeling of stillness, moments like that are devastating. But if you carry, somewhere in the back of your mind, the knowledge that the universe has never really been still, that planets spin, galaxies drift, space-time ripples, then the shock is a little less absolute. Motion is not an interruption, it is the baseline. That does not make upheaval pleasant. Knowing that Earth rotates does not stop you from getting dizzy if you spin in place, but it can shift the story slightly. Change becomes less of an exception and more of an expression of how things are built. When you lie in a dark room and think about all this, the ancient dome of stars, the slow surrender of geocentrism, the expanding galaxies, the ringing space-time, it can be overwhelming. There is a sense of being carried, of having never once stood on a truly unmoving floor. Which brings you to the last, quiet question that has been shadowing this whole journey. If nothing out there really stands still, not planets, not galaxies, not space-time itself, then where, exactly, can your mind rest? In a universe that has no final fixed point, is there any kind of stillness that is not an illusion? Maybe the answer is that there is no perfectly still place at all. Only moments where all the motion stops demanding your attention. And maybe that is enough. You have been traveling for a while now, from a pendulum in a stone hall, to clouds of dust flattening into star disks, to wheels of light held together by dark matter, to black holes dragging space-time, to electrons whose spin is not really spin, to a universe that, as far as we can tell, does not rotate as one. It is a lot to hold in a single mind. You are not meant to hold all of it at once, so let it shrink. Come back to something small and familiar. A room, with you in it. Maybe you are lying down. Maybe you are sitting in a chair that has learned the shape of your body. The ceiling is above you. Anonymous. The walls are just outlines in the dark. There is a faint noise from outside. Or maybe there is nothing at all. Feel, just for a moment, what is actually happening in that small space. Air brushes the inside of your nose as you breathe. Your chest rises, then falls. Somewhere under your ribs, your heart is squeezing and releasing, again and again, sending blood through vessels that have done this since before you can remember. Muscles in your face hold a little tension, then soften. Thoughts flicker and reform on their own. Under the floor, the planet is turning. Far outside the walls, the moon is moving in its orbit. The sun is carrying you in a wide, slow path around the galactic center. The galaxy itself is rotating, and the dark matter halo around it is helping to keep that rotation from flying apart. All of that is real, but none of it feels as real as the simple rise and fall of your breath. You are sitting on a rotating platform that is bolted to a rotating platform that is embedded in other motions you will never feel. The universe does not ask your permission to spin. It simply does. The only thing you are really being asked is, what do you want to do with the tiny circle of awareness you have right now? You could spend it fighting. Imagining the floor buckling, seeing yourself flung into space, thinking through every possible disaster, replaying every decision that led you here. You could mentally try to grab the universe by its axis and force it to stop so you can rest. Or you could, for a few minutes, let the spin be background. You do not have to like it. You do not have to be grateful for it. You just have to stop negotiating with it. The planet will keep turning without your approval. The galaxy will complete its loop without your help. Space-time will ripple or not ripple, regardless of how many times you replay old conversations. That can feel cruel. It can also feel strangely freeing. The people who uncovered these rotations did not have more control than you do. What they had was patience. Foucault could not slow Earth or speed it up. All he could do was hang a pendulum and wait, letting hours pass while the swing plane quietly turned. Penzias and Wilson could not switch off the cosmic microwave background. They could only clean pigeon droppings out of their antenna, listen again, and eventually accept that the hiss they heard was not a fault, but a message from the young universe. Jocelyn Bell Burnell could not change the behavior of a neutron star. She could only notice the odd scratches on chart paper, keep looking, and trust that the repeating pattern meant something real. None of them bent the universe into a new shape. They allowed themselves to see the shape that was already there. On a smaller scale, you have your own rotations, and some of them feel less noble. The morning routine that repeats until days blur. The cycle of work and exhaustion. The loop of worry, temporary relief, then worry again. Patterns in relationships that you promise yourself you will not repeat, and then watch yourself repeat anyway. The way your thoughts circle back to the same what-ifs when you are tired. It is tempting to see these loops only as traps, and sometimes they are, but they are also, in a quieter way, the scaffolding you grow on. The repetition of brushing teeth and answering messages and eating meals and going to bed does not mean nothing is changing. It means you have orbits. Within those orbits, things slowly shift. The question is not whether you can escape all loops. You cannot. The question is whether you can notice which ones are feeding you and which ones are only burning fuel. If you want, you can try a very small experiment right now, not a formal meditation. No need to sit in a particular way or breathe in a particular pattern. Just, for the next few breaths, pay attention to one loop in your body. Maybe it is your heartbeat. You do not even have to feel it directly. Just know that it is there, thumping away, like a personal pulsar, a star that evolved this strange habit of pumping instead of spinning visibly, ticking through your whole life without asking you to remember to command it. Or maybe it is your breath, a quieter orbit. In, pause, out, pause again. Let your awareness rest on that for a little while. Notice that the world outside your skin is still doing whatever it is doing. Notifications wait, tasks remain, galaxies spin, the microwave background hums. Somewhere, a neutron star is sweeping its beam across space. And yet, in this small slice of time, all that motion and noise has narrowed down to one simple cycle in your own body. Up, down, in, out, beat, beat. You do not have to hold it for long. A minute, half a minute, long enough to feel that there is a difference between the spin you can never touch and the loops that are close enough to sit with. When you let your attention widen again, nothing fundamental will have changed. Earth will not have slowed. Your problems will not have solved themselves, but the story in your head might have shifted by a microscopic amount. Instead of everything is out of control, it might be everything is moving, and I am allowed to be one calm point inside that movement. At least sometimes. If you like pictures more than instructions, you can use this one. Imagine a spiral galaxy in the dark, wide, thin, turning. From far away, it looks like a luminous pinwheel. Now zoom in your mind. Pick one of the arms, one of the faint streams of starlight curling around the center. Follow that arm until you choose a single, unremarkable star. Not the brightest, not the biggest. Just one of the hundreds of billions. Around that star, picture a small planet in a stable orbit. Nothing special. Maybe a little blue, maybe a little brown. On that planet, imagine a patch of land, a city, a street, a building, a room. The room you are in now, or something like it. In that room, a person lying down, or sitting, eyes half closed, listening to some quiet voice talk about spinning things. All of those rotations, the galaxy's slow wheel, the star's journey around its center, the planet's orbit, its daily spin, the eddies in its air, the dance of electrons in the circuits of whatever device you are using combine to create this ordinary moment. This breath, this sentence, this tiny chance to rest your attention anywhere you choose. Tomorrow, when you open your eyes, none of the cosmic motions will have paused overnight so you could sleep. The pendulum never really stops. But if, for a second, you remember that you are waking up on a moving platform in a moving galaxy, maybe whatever is waiting for you will feel a fraction lighter, less like a personal disaster, and more like one more pattern in a universe that never learned how to be still. And if tonight's journey helped tilt your perspective even a little, you can keep it. Save it somewhere in your mind or on your screen. And come back the next time your thoughts are spinning faster than the world beneath you. Let the universe keep turning exactly as it always has. And give yourself permission to close your eyes right in the middle of the spin.